So if you can share your screen,
Hello.
that looks great, and we can hear you. Okay.
Okay, amazing.
So you'll be telling us about moderate to high resolution spectroscopy of directly imaged exoplanets, and take it away.
Excellent. Yeah, so I had two projects I was pretty excited about, and they were very much related to about doing higher resolution spectroscopy of exoplanets. So I'm just going to go over both. So on one side, I'm going to talk about OSIRIS, which is moderate resolution spectroscopy. So ORA 4000. In here, the advantage is that there's actually a lot of data. I'm going to talk about the HO299 planets in particular, so that there's 10 years of observation on that system. And then I'm going to switch to KPIC, which is exciting. It's brand new. And I'm going to show results on behalf of the KPIC collaborations. But then we can do an order of magnitude higher spectral resolution of the same objects. So yeah, I'm going to get into it. Let's switch slide. Quick introduction slide. Why do we care about high spectral resolution? So the idea is that if we can resolve molecular lines, then first we can detect specific molecules, and that's also going to give us a better handle on their abundances. Also, with higher spectral resolution, we can break some of the degeneracy that exists at lower resolution when doing atmospheric fits between, let's say, clouds, surface gravity, and other things. Also, higher resolution spectra means we can measure radial velocity of planets, we can measure spin, so we can better characterize their orbital dynamic. And if we have very high signal-to-noise ratio spectra, for example, for bright brown dwarfs, we hope to be able to detect surface inhomogeneities, like, for example, clouds or around the planet with Doppler imaging. So that's something we hope to do with KPIC. So let me first start. My first half is going to be about OSIRIS. So this is work in collaboration with Quinn Konopaki, Travis Barman, Bruce McIntosh, Killian Wilcombe, and others. So doing moderate resolution spectroscopy of the HO299 planets. So like I said, we have been looking at these planets with OSIRIS for 10 years now. So a fraction of that data for B and C has already been published, but we got new exciting data on D. And the thing is that our entire data set provides very high signal-to-noise ratio spectra at moderate resolution of the three planets. So yeah, my job has been to try to reprocess all that data uniformly and try to do comparative planetology. So I'm going to show three different kind of results that we've done, that we have had so far. First, detecting specific molecules, then measuring the radial velocity of these planets, and measuring their carbon to oxygen ratio. And we care about carbon to oxygen ratio because we think that can help us understand their formation. So for example, the amount of solid to gas that was accreted during the formation might affect the CTO ratio. So to give you an idea of the kind of data and the quality of the data we're working with, here you have the combined high-pass filtered spectrum of HO299b. And I've also plotted molecular templates, so carbon monoxide, water, and methane for comparison, so you can identify the lines. And just as a detail, we're actually not fitting these extracted spectra. We're actually forward modeling the data directly, the spectral cubes, but it's just a detail. The idea is that if we take these molecular templates that are shown on top and we fit them to our data and with different shifts, radial velocity shifts, we can get plots like this, where we have a signal-to-noise ratio of the fit as a function of the radial velocity shift. They're like similar to cross-correlation functions. I mean, they're basically the same, just the forward modeling version of it. So each column here corresponds to a different planet, B, C, and D, circled in the image here, and each row corresponds to a different template. So the full atmospheric template on top, then strong detection of carbon monoxide and water, and no detection of methane in the planets. Nothing really surprising, just I'll mention that the lack of methane in these planets is a signature of disequilibrium chemistry, in particular for HO299b, which is smaller and cooler than C and D. So next thing we have been doing is measuring the radial velocity of these planets. So here you have all the different epochs for which, so in the y-axis, all the different epochs for which we have had detections. And if I combine them all, obviously the radial velocity kind of change over the 10 years, but just to give us an idea of the kind of precision we get, we can, if we combine them all, we get under kilometer per second precision, down to 0.4 kilometer per second for HRT9 and C. So I'm working on doing a proper orbit fit with that data. I don't have that to show yet, but in the meantime, I can show you that our data is consistent with predictions from direct imaging if you assume that the planets are coplanar and stable, you get the hatched posteriors here, and they're consistent with the data. Now, last but not least, the last thing I was going to talk about OSIRIS is measuring the CTO ratio for these planets. So Travis Bauman generated a grid of models, Phoenix models, varying effective temperature, surface gravity, and CTO ratio. And so we can fit that grid to our data. And here the best fit models are compared to the extracted spectra. So there's a lot here. So the top panel is K-band. So from top to bottom, you have B, C, and D. And then at bottom, you have H-band spectra. We have some H-band data for B and C. So if I fit the same model grid to low resolution spectra and photometry, the result, I'm going to go quickly here, but the result is I can get for each planet and each parameter, I can get 3 posteriors, one corresponding to each data set. So photometry, low resolution spectra, and OSIRIS. And what that plot shows is a difficulty to combine different resolution with grid of models, that ideally you would want all these posteriors to be consistent within each panel. Unfortunately, they're not. So I can't just multiply the posteriors to combine the data. So that work for the future, I guess. But we think we're pretty confident that the OSIRIS data is very sensitive to the CTO ratio, and the CTO ratio that we're measuring is all consistent with stellar CTO. So hopefully that can teach us something about their formation. Okay, so that's what we can do with moderate resolution spectroscopy. So now let me switch. What can we do if we go at R of like 40,000, so an order of magnitude higher? So that's a different collaboration that's led by Dimitri Mawet from Caltech. So there's obviously a lot of people involved that they are on the screen. I'm not going to mention them. But what is KPIC? So KPIC is actually not really a new instrument. It is a series of upgrades to the Keck instrument suite and AO facility that includes an infrared pyramid wavefront sensor and a fiber injection unit that feeds NIRSpec that we use for the high resolution in an infrared with a single mode fiber. So this slide is to illustrate the challenge of doing high contrast in general, so both imaging and spectroscopy, is that on the right you have that animation of the HRT9 planets orbiting the star that you've probably seen before. But what you need to remember is that each image there is a heavily processed data set in which the starlight was removed to highlight the planet signal. But in truth, a raw image looks like something on the left. And the planets there are anything between 10 or 1,000 times fainter than the starlight at their separation. So we want to do spectroscopy of these planets. Most spectrographs use slits. Here we're using a single mode fiber, and there are two advantages, at least I can think of right now, of the single mode fiber, is that first, it's going to give you a very stable line spread function of the detector, and also it's going to reject more starlight than a slit would. So if you place the single mode fiber at the location of the planet, the single mode fiber would couple very well with a point source, but will not couple as well with the starlight than a slit would. So it's going to be easier to detect the planet. The challenge, obviously, of a single mode fiber, like I said, we need to place it at the location of the planet. So that means two things. We need to know exactly where the planet is. Fortunately, most directly imaged planets have pretty well constrained orbits. And we also need to be able to blindly offset the instrument pointing to that companion. So here you have an illustration using a stellar binary, so where we can see what we're doing, and we've shown that we can offset to 2.5 arc seconds by using less than 2% throughput. So so we can do it. There's more than one fiber. What we usually do is put one fiber on the planet and align the other fibers to sample the starlight. So we're just aligning it with closer to the star, and we use it for calibration purposes. For example, to model and subtract the starlight in the planet to star fiber. So that's what it looks like on the detector. So you have a fiber per trace. So one of the important plots, one of the most important property of the instrument is its throughput. So we're limited by the throughput of the instrument. And here is to show you how much work was put by the instrument team in getting this to work. From last year to this year, we got 2 orders of magnitude increase in throughput by solving some problems that I don't have time to get into. But the highlight is that we have reached our goal of 2% throughput, and we actually got better than that, 3% during the last run. And that was what was necessary to do the science that I'm going to quickly mention here. So everything is super preliminary, but just as a sample of the data, here you have the CO band head for HRS-99D, and we can forward model the data. We build a model of the planet, we build a model of the starlight, we jointly fit them. Here, Jason plotted both components separately, and you can see that, for example, D is 10 times fainter than starlight in that data. It's even worse for E. It's like more than 100 times fainter, but we have been able, despite that, we could detect them pretty easily. So we got detection of CDE. So you have the cross-correlation functions on top, measurements of radial velocity, and very exciting, we think we might have spin measurements for the HRS-99 planets. So that we're still learning how to calibrate the data. That's work led by Jason Wang. So stay tuned for what's it's going to come soon. Also, we have looked at other objects. I'm running out of time. I apologize for that. I'm going to go quickly. Just last slide. So that was KPIC1. So this is it was a bare minimum to do high contrast, high resolution spectroscopy of exoplanets. But KPIC phase 2 is going to come soon. So it's going to involve a new DM to do spectral modeling at the location of the fiber, better throughput with an atmospheric dispersion corrector and beam shaping optics, and also an experimental mode to not only do characterization, but detection of planets at half lambda over D. Sorry for running over, and that was it. Thank you.
Okay, excellent talk. Super exciting to hear what KPIC has been up to and about these new upgrades. Again, I will remind folks that if you have questions, please pop those in the channel for this session over on Slack. I'll start off with one while we wait for other folks. So you mentioned in the first half of your talk that you're working on a proper orbital fit for the 8799 planets. I'm curious what goes into that, and is it based solely on the OSIRIS data that you were showing, or are you combining other observational sources as well?
So what I'm looking into right now is just fitting the direct imaging data that has already been published. So Jason actually did a lot of work a year or two ago, combining a lot of the astrometry. So I was going to try to see what we can get by fitting that direct imaging astrometry with the radial velocity measurement and see if we can constrain better, for example, the inclination of the system. But I don't have, my MCMC chains have not converged yet, so I don't have anything to show.
Gotcha, I feel you on that pain. And then another question that I'll just keep running the floor. Can you talk a little bit about the coupling efficiency of the single mode fiber? Because I know that's a thing that we struggle with sometimes on the radial, like PRB side of this. I
guess what do you want to know? I'm on the end side of the instrument, so I'm not the one touching the instrument. I just enjoy what they've reached. So I know the throughput end-to-end is 3% now. It's going to be better with KP2. They have had to overcome a few challenges. So there was some alignment problem in the instrument that was hard to pinpoint. There was an AO stop also that had to be changed that we were not aware of, but it's all I know. So
that was a pretty solid answer. I'll take that. Do you have any targets that you're especially excited about going after once the improvements at KPIC have been implemented? Does it open up different?
I mean, we're not going to wait until the improvements are done, but I mean, all the direct imaging planets are game on. So, and yeah, any direct imaging planets that you can come up with, we're probably going to try.
Okay, good stuff. With that, we will say thank you again for an excellent talk and move on so that we stay on time.